And here we go with another example of hypothesis testing for proportions. So this one says, in a survey, 65% of the respondents stated that they keep their pets up to date on all vaccinations. A veterinarian believed this result to be inaccurate, so she randomly selected 150 pet owners from her clinic and discovered that 112 of them are fully up to date on their pets' vaccines. Does the veterinarian have enough evidence to say that the proportion of pet owners that keep their pets up to date on all vaccinations is different from 65%? Use the alpha equals 0.01 level of significance. So looking at the given information, 65% of the respondents state that they keep their pets up to date on all vaccinations. The veterinarian randomly selected 150 pet owners. 112 of them are fully up to date on their vaccines. Does the veterinarian have enough evidence, is what tells us that we're doing a hypothesis test. Proportion, and then let's see, different from 65%, and then alpha equals 0.01 level of significance. So we're looking at proportions, so P, X, N, alpha. It doesn't look like I was given P hat, so I'm just going to do X and N. So P is going to be 65% from the previously stated survey, which is 0.65. X is the 112 pet owners that have their pets fully up to date. 150 pet owners were surveyed, and our alpha is 0.01. So first thing we need to do is write out the null and alternative. So we start with our HO and our HA. Our HO will say that P equals 0.65, and then our alternative is that P is not equal to, because of the word different, 0.65. Step 2 is the test statistic. So that's using our z-score for proportions. P hat minus P divided by the square root of P times 1 minus P divided by N. I have P, I have N, I don't have P hat, but I have what I need to find P hat. So P hat is X over N. My X is 112. My N is 150. 112 divided by 150 is 0.746, repeating on and on and on and on and on. So I'm going to write down 0.7467 for my P hat. I'm going to go to at least 4 decimals on my P hat. 0.7467 minus 0.65. That's the top, and then the bottom is the square root. 0.65 times 1 minus 0.65 divided by 150 is our N. So 0.7467 minus 0.65. The top is 0.0967. And the bottom, oops, is 0.0389444,048. So we do that last division and we get 2.483. So now this part, the p-value, is a little bit different because we're doing a two-tailed test. So I do recommend drawing the picture on this one if you haven't been. So the p-value here we have our curve, 2.483 would be maybe about here. And then it's a two-tailed test, not equal to. So what I'm going to do is I'm going to find everything above 2.483. But because it's not equal to, there's a chance that it could have been too high or too low. So then what I'm also going to do is I'm going to take negative 2.483 and I'm going to shade everything below that. And so now I have shaded the two tails of the curve. I shaded the tail above the test statistic, and then I shaded the tail below the negative of my test statistic. So these two areas combined are going to create my p-value. So when I go to calculate the p-value, what I'm actually going to do is I'm going to focus on the negative. So I'm going to do norm.s.dist negative 2.483, comma, true. And I'm going to focus on the negative because I'm looking at the area to the left of the negative. And so I don't have to do a 1 minus. If I were to focus on the purple area that I have here, the positive 2.483, that's the area to the right. So I would have to remember to do the 1 minus. By focusing on the area to the left of the negative z-score, I don't have to do any of the 1 minusing. So let's take a look at what that gives us. So I'm going to go down a box. So equals norm.s.dist negative 2.483, comma, true. And I hit enter and I get 0.006514. So I'm going to write that back into my notes. 0.006514. So that's this area. And then because of symmetry, the normal distribution is symmetric, this area is the same. The area less than negative 2.483 is the same as the area greater than positive 2.483. So my p-value is 0.006514 times 2. I have to find both areas when I'm doing a two-tailed test. So I'm going to take the area I found and I'm going to multiply it by 2. And I get 0.013028. That's my p-value. So basically, because we couldn't decide, or the veterinarian in this case couldn't decide, is it less than or is it greater than, and said, I'm just going to see if it's different from. We have to consider both possibilities. Could it be too small or could it be too big? So now we can come down to 4 and we can look at the conclusion and then write out the interpretation. So the conclusion we want to know is our p-value less than our alpha. We want to know, is this probability too small to be possible? Is this a significant result? And it's significant if it has a small probability. So is 0.013028, I'm just going to use all the decimals, less than, and what was our alpha? 0.01. So again, I'm going to look a digit at a time. Those are both zeros. And then we have our decimal point. And then I have zeros again. And now I have a 1. And now I have a 3. And then after this 1, if I erase that question mark, this would be a 0. So my p-value is not less than. My p-value is bigger. So my p-value is not low. So we are not going to reject the null hypothesis. And then writing out the interpretation, we do not have enough evidence to conclude that the proportion of pet owners that keep their pets vaccines up to date differs from 65%. So we did not have the evidence we needed to prove what we were trying to prove. And what we were trying to prove is that the proportion of pet owners that keep their vaccines for their pets up to date is different from 65%. We were not able to prove that because we did not have a small enough p-value to show that our results, which was 74%, were significant for this test. So this is a hypothesis test with two tails.